Chapter 10, Rigid Body Dynamics, Part A, Review of Rotational Dynamics in 2D. We'll start with a brief review of rotational kinematics and dynamics from Physics 203. Remember that the linear distance, velocity, and acceleration are related to the rotational counterparts by multiplying them by r. So if linear tangential velocity is r times the angular acceleration, and the linear tangential acceleration is r times the angular acceleration. The case for a position is slightly different. S is the arc length along the curve is equal to r times theta. Each of these quantities can also be expressed as a vector. So the vector angular position theta, angular velocity omega, or angular acceleration alpha can be thought of as a vector where the vector is directed along the axis of rotation using the right-hand rule. You may also recall that when you first learned about rotational dynamics in your first year physics class, a lot of the same equations hold, except that you replace the linear variable with a rotational equivalent. So the linear inertia is simply the mass. The rotational inertia is given by the letter I. We'll talk about this more in this lecture. The force is replaced by the torque, and the torque is the position vector across the force vector. The momentum is replaced by the angular momentum. Newton's second law has forms. Newton's second law can be written as the equivalent of F equals ma, that is, the torque is I times alpha, or the force is the time derivative of the linear momentum is replaced by the torque is equal to the time derivative of the angular momentum. And kinetic energy 1/2 mv squared is replaced by 1/2 I omega squared. So we'll go through some of these quantities in the next few slides, but this is just like an overview, which you've probably seen in Physics 203. Okay, so let's start with an example. Let's look at a physical pendulum. So we've got a rod with a uniform density hanging from a pivot point, and it's going to swing back and forth. So as it swings on the pivot, the question is going to be, what is the angular frequency or the period of the oscillations? So let's see here. We'll assume that the pivot point is right here. The center of mass is going to be assumed to be at the center of the rod since it has a uniform density. And the distance from the pivot point to the center of mass we're calling A. So we're going to assume we swing the rod over by some initial angle, let it go, and then watch the oscillations. We want to find the oscillation period and then find the length of a simple pendulum that gives that same oscillation period. So if you had just a pendulum bob with all the mass down at the end, how long would that pendulum have to be to have the same period as this solid beam that's hanging? Okay, so let's analyze this. This is again using methods that you've probably seen in 203. So m is the total mass. The center of mass, we're taking it to be the very center of the rod. A is the distance from the pivot to the center of mass point. When gravity pulls down on the rod, you may remember that it acts on the center of mass of the system. So this x is going to be the halfway point along the rod. And so we'll have the force vector pulling straight down with the total mass of the rod times g. I will be the rotational inertia of the rod around the pivot point. We'll come back to that. We can write the torque due to this force around the pivot point as r cross the force of gravity. So r would be the vector going from the pivot point to the point where the force is acting on the object, so to the center of mass. And it's negative, meaning that it's going clockwise. So counterclockwise is usually taken as positive torque, just like positive angle. The negative sign means it's going to be going clockwise. All right. So to figure out the cross product, the simple way of doing it is to extend the force back along the line of action, and you take the perpendicular distance from the pivot to that line. That perpendicular distance is r perp, and that turns out to be a sine theta. So if a is the distance here, that's a right angle. So this side of the triangle is just a sine theta, where, again, using some geometry, if that angle is theta, then this angle over here is also theta. So we can write the torque as just negative the force of gravity times that perpendicular distance. We plug in a sine theta. We plug in a sine theta for r perp, and then mg for the force of gravity with a negative sign out in front. And so that gives us the torque. We can now use Newton's second law that says that the torque is equal to the moment of inertia times the angular acceleration. So we're not going to worry about the vectors. We're going to assume that all the angular vectors are pointing perpendicular to the page, or coming out of the page. So we have moment of inertia times the acceleration is equal to the torque. So we're just plugging in this for the torque, set it equal to I alpha. We'll next use the small angle approximation. So we'll assume that if you only pull the pendulum over a little bit, you can approximate sine theta with, that's approximately equal to theta. So we get an equation of motion. Remember that alpha is just the second derivative of theta with respect to time. So we replace alpha with theta double dot and then divide through by the rotational inertia I. And then we're also replacing sine theta with theta. And I've also moved this term over onto the left-hand side of the equation. So this is the equation of motion you get once you do all that. If it's not clear, then I recommend you go through and write out all the steps to make sure it's clear. This is in the form of a simple harmonic oscillator. So you have the second derivative plus a constant times the same thing equals 0. So the constant out in front of the theta is going to be the angular frequency of oscillations squared. So if we take the square root of that, that gives us the angular frequency of oscillations. Okay, so we haven't evaluated what the rotational inertia is yet. You may remember tables like this in Physics 203, where if you have different shape objects spinning around an axis, here's the rotational inertia for each of these different objects. Our object is the same as a thin rod with length L. So if you spin this rod around its center of mass, the moment of inertia, or the rotational inertia, is 1/12 ml squared. So we're going to use that to plug in for I. So we want to evaluate the rotational inertia, but we want to evaluate it around the pivot point, not the center of mass. So we know that the rotational inertia around the center of mass is 1/12 ml squared from that table. To figure out, which would be around this point right here, to figure out what the rotational inertia is around the pivot up here, we use the parallel axis theorem. And that says that the rotational inertia around any other point other than the center of mass is equal to the rotational inertia through the center of mass plus ma squared, where a is the distance you translate, is the distance from our point away from the center of mass. So So A matches this A. The rotational inertia through our pivot point, then plugging in 1/12 ml squared gives you this. We can now plug in our pivot point into the angular frequency formula we found. We get that. And if we simplify a little bit, the masses cancel out and you get this final expression. So that's it. That's the angular frequency of our rod. So we found what we wanted to. We want to now compare it to a simple pendulum. So here's the result that we just derived that, well, we just found that the angular frequency, the period of oscillations is 2 pi over the angular frequency. We'll plug in for omega. Let's go back. So we see that the angular frequency is GA divided by 1/12 L squared, all that kind of stuff. So we see that omega is on the bottom, so we just like flip this expression upside down. So the L squared is on top and the GA is on the bottom now. All right, so that's the period of oscillations. Remember that the period of a simple pendulum is 2 pi square root of L over G. So what we want to do is we want to find the length of our pendulum L so that our simple pendulum has the same frequency as this one up here. So we just set these periods equal to each other and solve for L. And when you do that, if you set these two things equal, the 2 pi's cancel, this 1 over square root of g's cancel, and what we have left over is L equals this thing over A. So we get this right there. So the length of the simple pendulum is A, the distance from the pivot to the center of mass point, plus this extra little bit. So 1/12, basically L squared over A. All right, so let's look at an example. Let's assume that the distance from the pivot point to the center of mass is 3/8 of the overall length. So that means that it's if you take the distance from the center out to the edge, it's about 3/4 of the way from here out to there. So the overall length would be 3/8. Anyway, so that's where we're putting our pivot point. We calculate the length of a simple pendulum that would have that same period from the previous slide. So we just plug in A equals 3/8 here, and we get it's about 60% of the total length of the pendulum. So from here down to here would be 60% of the total length. All right, so let's play it and see how this looks. So you see that if you design a simple pendulum with just that length, then it'll swing in synchrony with the original bar that's hanging from the pivot. It doesn't work to create a pendulum that's at the center of mass, right? So if our center of mass of our pendulum is here, and we hung a pendulum down with the length equaling A, so if the length of our pendulum is just equal to A, the distance from the pivot to our center of mass point, and let that system go, they get out of sync pretty quickly. Right? And so, of course, the difference is that the two pendulums have different moments of inertia, which affects the dynamics. We could also go through and analyze the problem using Lagrangian techniques. Since we've been doing that, I'll just briefly show the results. So we've already calculated the potential energy. Well, we haven't. So the potential energy you could figure out just from the height of the center of mass point. So it would be mga cosine theta, negative sign. So that would be this height right here down to the center of mass point. The kinetic energy, 1/2 I omega squared, where omega is theta dot. So this becomes the Lagrangian down here. The Euler-Lagrange equation for theta would be this. Once you plug in the Lagrangian into the Euler-Lagrange equation, this is the equation of motion. It's the same equation of motion we just saw. So whether you like to work using energies or forces, you get the same result. Again, use the small angle approximation, you get this, and you get the same angular frequency. Okay, so now let's talk about angular momentum a little bit more. There are two ways of writing angular momentum, which you're familiar with, I'm sure. The first way is saying that the angular momentum is just r cross p, that is the position vector cross the linear momentum. So if you had a mass m and it's going in a circular path, instantaneously the position vector is coming radially outward. The momentum vector is tangent here. So when you do the right-hand rule, r cross p, you're going to get a angular momentum vector pointing straight up out of the plane. So the other expression you might have seen is that the angular momentum is the moment of inertia times the angular velocity. So L equals I omega. So in this case, if you have a symmetric top and it's spinning around the z-axis, the angular velocity will be pointing along the z-axis and the angular momentum will also. Okay, so the first result is general for a point mass. This is always true for a point mass. That's a solid result. The second result, however, only works when the object is spinning requires no external torque to keep it spinning. Okay, so if you just have a top and it's perfectly balanced, there's no torques acting on it, it can just spin like this, then this is a true statement. However, if you have an object that's like lopsided or is spinning along an axis that isn't a symmetry axis, then it turns out that this expression is not true. We need to make a more generalized version of this statement. And what we're going to have to do is replace the moment of inertia I with the inertia tensor. And then this is true, but if I is a scalar, this only works when there's no external torque. All right, so let's look at an example. So consider two objects, two masses, and they're spinning around in a circular path. So the angular velocity vector is pointing along, let's call this dashed line the z-axis. So the objects are spinning around the z-axis, and let's see what this looks like. So you can see the object spinning. The position vector is in red. The angular velocity is in magenta. Okay, let's look at the angular momentum vectors for this case. Remember, let's see here, the position vector is in red. I'm going to draw in the velocity vector in blue as this thing is spinning. So it's spinning around. The blue velocity vector is right there. So when you calculate r cross v, you get a vector that's pointing upward with those green arrows. And now if you calculate the total angular momentum, you add those two together, it's going to have just twice the length along the z-axis. So the total angular momentum is just the sum of these two things. And we see that the angular momentum vector is in the same direction as the angular velocity vector. And again, we haven't proven this yet, but it turns out that the angular momentum is parallel to angular velocity whenever the external torque is zero. So you don't need a torque to keep this system moving like it is. Okay, so now let's look at a case that's a little bit different. We're going to displace the circular motion of each particle vertically along the z-axis. So one will get shifted upward by some distance, and the other one will get shifted down the z-axis by the same distance. Okay, so now our position vectors are at an angle here, and the velocity vectors are they're the same as before. They're going around the circle. Because each of these objects is spinning around the z-axis, the angular velocity vector is going to be the same as it was before. It's just like spinning around in the same way. So this is still a rotation around the z-axis. Let's now look at a slice through the previous diagram where this is our object up here, as our object down here. This velocity is going to be into the page as it's circling around. This one's coming out of the page as it's circling around. So the angular momentum vector is now going to be an angle in this case. So if you remember, the position vector is going to be tilted in the plane now. So R1 is going like that. The velocity or the momentum of the first one is going into the page. So when you take the cross product of this cross a vector going into the page, you get a vector that's at an angle. It's going to be perpendicular. This is going to be a perpendicular. That's going to be 90 degrees right there. And the angular momentum vector is going to be pointing out like this. Similarly, R2 is going to be coming down here, but now P is coming out, and so if you use the right-hand rule again, you can convince yourself that L2 is going to be parallel to L1, so they're going to be pointing in the same direction. These two are actually the same vectors. L1 equals L2. So in this case, the angular momentum vector L, when you add these two together, right, we're going to get angular momentum vector that's twice the length. So this would be the total angular momentum vector like that. So the total angular momentum vector is not parallel to the angular velocity vector. L is not parallel to omega. So what that means is this system does require a torque to keep it spinning like this. All right, let's see what this looks like in the animation. So there are objects tracing out circular paths that are displaced from each other vertically. There's the velocity vectors are in blue. The angular momentum vectors for each particle is in green. And now we're going to add them together to give the total angular momentum vector. And finally, the torque. We're going to draw in the torque. We're going to come and derive this a little bit later, but the torque is now given in that kind of dark purple color. So the torque from Newton's second law, it says that the torque is the time rate of change of the angular momentum. So because the angular momentum vector is spinning around like this, instantaneously this vector is going to be moving along the circular path. So the tip of this angular momentum vector is going to be coming out in this direction. That's why the torque is angled in that direction. Okay, so summarizing, if the angular momentum and the angular velocity are parallel, no torque required. If the angular velocity and the angular momentum are not parallel, you need to apply an external torque to keep the system spinning. Here's the expression. I'm using a capital gamma for torque. So yeah, this is just kind of what I explained before. Since the angular momentum is spinning around like this, instantaneously it's going in this direction. So that's the direction that you have to apply the torque to keep the angular momentum changing like that. All right, an interesting question for you is what happens in this system? You've got these dumbbells, one spinning around up here and the other one spinning around down there. What would happen if you removed the external torque? So if you didn't have the torque in place, how would this system evolve? That would be something maybe you could like think about this on your own, see if you can figure it out. We'll talk about this in class. Okay, last example. Let's now consider the case where our pivot point is down here. Both objects are now spinning around the z-axis, but now they're in the same plane. So they're in the same plane, but that plane doesn't contain the pivot point, at the origin. So our position vectors are kind of angled up like before, but these things are both on the same plane tracing out this circle. So the question is, in what direction does the total angular momentum vector point? And is an external torque required to maintain this motion? So see if you can figure this out, and we'll talk about this example in class. All right, that's it.